Thank you, Eli. And I want to start, as others, by thanking the organizers for this. Organizer, Emanuele, and his emotional support, okay, for this great event and for the invitation. So Martinez said to talk about noise, and I will indulge him a bit in this talk. And I want to start with this sketch. I have a very gifted postdoc, and I like to challenge him every now and then. So once I asked him to draw something about thermodynamics, and he did, something very nice. And then I tell him, do something about quantum computers. And I gave him this to start with. And this is what he came up with. It's still a sketch, but you can see the zeros and one immersed, and the interference, and it's all on the chip, and there are the control wires. And it's not for a cover of a journal, okay? This is for my office. Okay, that's the topic of my talk, but before that, a little bit about us. So these are the topics we're working on. Tanmoy is working on diagnostics and also Mujahid, and Ivan is working both on error mitigation and on quantum thermo, and Jadar is working on error mitigation. Good, so first let's set the basis and see what can quantum computers do right now. So this is something I ran on the Lagos IBM chip, okay, which is relatively good. And just a basic 3-qubit Fourier transform. And then I immediately implemented the inverse, so in the end it should do nothing, okay, just the identity operator, ideally. I also omitted these swaps at the end to reduce the noise a little, okay? And so it's equivalent to something like 18 C-naughts. And we measure the overlap with the initial state. It's the identity operator, so the overlap with the initial state should be 1, right? And do you care to guess what the number is?
5%.
Huh?
5%.
Go up.
20.
Go up.
0.999.
Okay. So here it is, okay? And really, it's not like this machine is very impressive and you can do quite a lot with it, but in the end, when you want to calculate even something simple, it's not trivial. You have to do something for it, and obviously, I wouldn't trust it in its present form with a computation that I don't know what the output should actually be, right?
But it's in the positive direction, and it's an important statement. It's not 0.5, it's 0.57, and it's not 0.43.
It's 0.57. On average, it was 0.53 once and 0.59. This is
the
average.
average was 0.5 or higher than 0.5?
No, the average should
0.57.
be 1/8, right? If it's spread uniformly between 3 qubit states.
It wasn't random, that's the question. You saw a signal beyond random.
Yeah.
It's good.
Yeah.
Random would be 1/8, right?
No, it's within the, yeah, but still, you wouldn't trust it for actual computation. So the thing is with these devices, these NIST devices, they are not good enough to be used as is, I mean, without additional components, and they are not big enough and clean enough for error correction codes. So one of the leading solutions now is to actually implement quantum error mitigation, which I'll talk about. However, it's more than just an intermediate solution. It can also help in the long run to reduce the hardware overhead in error correction codes, and we start to see some papers about this. And also, since it's not based on a specific algebra or a specific structure, it can be implemented also in an analog system and for sensing and for imaging and so on. These devices have 2 types of noise, which can occur either during the preparation stage, the evolution, or the measurement. I will focus on the evolution, okay, that's the most problematic part. And one type of noise is called coherent error, and essentially the idea is it's essentially miscalibration. We intend to run a certain unitary, and we consistently implement another one, okay? So it could be, for example, on the Bloch sphere, it could be over-rotation or under-rotation, okay, but it's still unitary evolution.
But what if it's not the same? A
The same as what?
A unitary evolution, which is always a little different.
That would be in that category, because it will be a Krauss map. If you throw a coin and then implement either this unitary or this unitary, it's already a Krauss map, it's incoherent noise. Okay? And noise in the control is incoherent error, okay, if your control fluctuates. But this is a constant drift, okay, the miscalibration essentially.
So in theory, I could measure someplace else classically and correct for it. Because the actual quantum state is still pure.
Yes, I mean, if you have this information, right.
Inconsistent,
If you have the information, you might have, you may need to run actual another quantum circuit, which might be of the same length to correct it, but in principle, yes. And the other type of error is incoherent error, which is essentially coupling to the environment, which is in general not very well known in quantum computers, some cases more than others, but it induces a non-unitary evolution in the subspace of the computation. And it's very important to distinguish between these two types of errors because they have completely different solutions. I mean, here one solution is just to improve the hardware, and of course people are working on it. While in coherent errors, a very good solution is to do randomized compiling, which essentially is running the same circuit with different variation, and this somehow averages the coherent error. And what's nice about it is that it actually converts there's no free lunch, it converts the coherent error into incoherent error. Okay. And therefore, it will suffice to focus and talk, at least in this lecture, talk about incoherent errors, okay? Because we will do this reduction, and actually, in all the experiments I show you, we do randomized compiling to cope with the coherent noise because it's very there. It can be quite strong. Let me just mention that there is no presently a very effective way to measure incoherent error in a scalable way. Okay, this is a standing challenge, and you can take a look at this paper where we try to make some progress along this direction. And the idea in quantum error mitigation is essentially to run additional measurements to study the noise, and with this information somehow to mitigate it. And this can be done by different techniques. The point is that many methods are not scalable. They're potentially very good, like probabilistic error cancellation and so on, but they are not scalable. So usually they are limited to 2 qubits, maybe a bit more, and that's it. So there is a method that is not sensitive to the scale, which is called zero noise extrapolation. And in particular, a variant of it that is called global folding or global unitary folding, which I'll present in a second. And as I said, we will ignore the coherent errors, but they're always there. So what is global folding? Let me show it on a CNOT, and you'll get the idea. Let's say that this is the whole circuit that we have, and we measure some noisy expectation value. Okay, this is not an ideal gate. Then we take the circuit, we create its inverse, and then again the circuit. So this is, the CNOT is the inverse of itself, okay? But essentially what we prepared here is the identity operator. However, in terms of noise feature, it should be similar to this one, because it's prepared from the same elements. And then again, we measure the expectation value, and we do it with 5. So roughly speaking, we have 1 unit of noise, 3 units of noise, 5 units of noise, okay? And it sounds heuristic, and it is, okay? There's no, it's a heuristic method, but it's quite nice. The idea is to put these values on an axis, and so here's 1, 3 units of noise, 5 units of noise, and of course the ideal value, which we don't know, is supposed to be here, 0 noise, okay? So if we have 2 measurements, we can extrapolate towards 0, okay, and get some estimation of the correct value. And of course, if we have more points, we get closer to the value, and so on. And what's nice is actually that these coefficients do not depend on the details of the circuit. Just you see some combinatorial coefficients, and You can put it in a table, you can calculate it, but there's no resources going into calculating these coefficients. If it's not a C-naught, it's an actual circuit, the idea is the same. Let's say we have this circuit. To create the inverse, if we have a C-naught, we just keep the C-naught. If we have single qubits, we change the sign of the angle, okay? And that will create, ideally, the inverse of this. So this is, looks like this when we have an actual circuit. And the point is that this method doesn't work, okay? It looks really nice, but it doesn't work. And I'll show you experiments, but it works only in a very specific case that is called a global depolarizing channel, which is highly unphysical. Okay, we have T1, we have T2. It's not global depolarizing channel. And just so that I will not, seem like a madman shouting that it's incorrect, we find more and more confirmation for this. This is taken from a paper by IBM, where in the appendix they talk about this method. They don't use it, but they talk about it. And they say that at least arbitrarily deviate from the desired result when the noise is not global depolarizing. Okay, so I think it's consistent with what we find. More than that, the performance limit of this method are unknown. It seems like if we keep going to higher orders, okay, we will have better and better approximation of the actual value. So the theory doesn't tell what are the limitations. And also in terms of, I wouldn't say it's terribly costly, but it's possible to do better. Okay. And essentially, more shots, it's not just about the time and the queue and how much you have to wait. It's essentially your noise parameter can change during the evolution, and that's a challenge for all error mitigation techniques. Okay, and now to our method. So the first essential ingredient in our method is we started really from the master equation, okay, a rather general one, and we realized that to make it work, we need to replace this circuit inverse that I've shown before with the pulse inverse. So the pulse inverse means that you take all your control signals and you reverse the schedule and take all the, change the signs of all amplitudes. In the absence of noise, it will generate U dagger. Okay? Now, there are many ways to generate U dagger. It's not unique. But if you want to cancel the noise, it has to be done in a specific way. So the road to implementing this unitary is very important. And what we assume about the noise is that it's being reversed without a sign change. So it's not an independent assumption. It's something that essentially follows from this. First, about the sign, it doesn't change because it's not like if we run things in reverse, decoherence will turn into anti-decoherence, right? So it will still be decoherence. And about the flip of the reversal of the schedule, so think about running several noisy elements sequentially. If we reverse the drive and we first run this noisy gate, okay, so the noise will be reversed as well. Okay, so that's essentially the idea. So we allow for time dependence. There's no problem that the noise will change from here to here. This is absolutely not a problem, but it has to follow this. Okay?
Do you understand that you're assuming that there's some sort of time symmetry? Right?
No, so the noise doesn't have to be symmetric.
No, not the noise, the unit, Hamiltonian.
The Hamiltonian? No, it could be as shown here. Okay? It doesn't have a specific time reversal.
No, but you're assuming that by basically reversing all the controls, you're going to get a dagger.
Ah, okay. So you really need to change all the terms in the Hamiltonian for this to happen. You cannot change that. If you have, let's say, a bare Hamiltonian and also controls, you cannot change just the controls. So it has to be in some already rotated frame where you can control all the degrees of freedom, as happens in, in the IBM processors. And once you change actually all the signs, then it works. You can't change only part of it. Actually, this can be exploited for something if there are terms that do not change the sign, but it's outside the scope. So under this, using this pulse inverse, we derive this equation that we call the kick equation, which relate the noisy forward evolution and the noisy backward to the noiseless evolution, and there is a correction which is second order in the noise. So let me just give a glimpse on how we do this. We go to the interaction picture in Liouville space, you're familiar with it, and then essentially we do a Magnus expansion for the noise. You can see here the first term. This is the noise in the interaction picture, and it's time dependent because we go to the interaction picture. This is omega 1, and this is omega 2. It's already second order in the, in the noise. And this is what we throw, all the high order terms. Okay, so we keep only this. And from here, we derive this equation. Now, if I'll go to one of the experimentalists and ask them to do 1 over square, you know, it will be the end of the relationship. So we need somehow to translate it into an operational protocol. And the idea is to turn it into some power series, because now each element you can interpret as either backward or forward, and you can run it. And it has a clear operational meaning, which is somewhat similar to this global folding, okay, going backward and forward. So the simplest way of doing it is, as shown here, we just add the identity, add and subtract, and then we have a term here which is essentially small, because you know, we're going forward and backward, and if the noise is not extreme, we're still close to the identity. And then we can do a Taylor expansion around 0, and therefore we get this, this expansion depending on how much, where we truncate the series, so we can get a first order mitigation, second order mitigation, and each term here is a different experiment. Okay? You cannot combine them because they have pluses and minuses, so it's really, this is one measurement of expectation value. This is the same as was in global folding. So now we compared, you know, the coefficients that we got here compared to, sometimes it's called in global folding Richardson extrapolation, never mind, but it's this polynomial fit. And to our surprise, it was exactly the same coefficients. Okay? So we're not doing, our method is not extrapolation. If anything, it's more like interpolation of this function, or approximation by a Taylor series. But it led to the same result. We were, you know, it's mixed feeling about this. But of course, we use the pulse inverse, and I'll show you how much it's important. And the second thing is that this is only the first stage of our theory, which is suitable for weak noise. And I'll show you that we can go beyond that in 2 slides. So here is an experiment. This was in Jakarta. Jader ran this experiment, 10 swaps, 30 C-knots. And he compared how it looks when you're running the pulse inverse or the circuit inverse, again with this Taylor expansion. Okay, so this is still not you know, the final stage of our theory. So what you can see here, this is what we get. Okay, so the observable is as before, the survivor probability. Okay, just we had to pick something, and initially without mitigation is 0.8. Okay, we call it moderate noise, just a name. And you can see when doing the circuit inverse, okay, it strongly deviates from the target. Okay, and with our protocol, it converges. And I just want to point, you know, to this. If you just run iteration, it looks like boom. Okay, but the point is that one should verify by running another order, because this type of miracles happen. Okay, that. It looks like you get a very good mitigation, but it's inconsistent. You run it with different initial conditions or something, and then you see that it's not robust. It doesn't work.
Can you remind again what exactly you did before the original?
So we prepared it in the, okay, in different initial conditions, actually all the computational basis, and we measured what is the probability to be in this state. So again, it should be the identity 1.
After
Okay.
10 swaps.
Yeah.
This is the point at 0. This I understand.
Yes, and here we applied this forward, backward, you know, this protocol.
But
Okay.
you applied during, after the circle, so you applied what? At
Okay,
n equals
yeah.
1. You
So
can show
for n equal 1, we applied this. That means we ran k, okay, just forward. We measured the survival probability, multiplied by 3/2. Then we did forward, backward, forward, measured the same observable, multiplied it by -1/2, and combined them.
So forward, backward, forward is a very long 30 swap circuit.
Just forward is 30 swaps. Forward, backward, forward is 90.
90 single.
Huh? Yeah, yeah, yeah. So it looks like we're working with very noisy values, but in the end, what we want is to learn about the noise. So it's
So again, it's a form of extrapolation in the sense that you're taking a decaying, as you go to higher order, the survival probabilities go way down, obviously. So this is an interpolation formula, more exact.
exactly. So again, it's more interpolation than extrapolation, but you know, that's. I think the point will be more clear where we deviate from the previous notion. Was there another question? Yeah, Declan.
You also tried to pulse stretching and not like global folding?
No, we didn't. Pulse stretching, you know, we saw that it, you know, it didn't pick up, although there was recently, not that recently, this paper I showed, they actually used pulse stretching. I don't think the results are that impressive, but they did it for many qubits. The point is that in pulse stretching, there is an assumption that the noise is fixed in time, okay? And leakage noise, for example, is something that is inherently time-dependent. It's caused by non-adiabatic couplings, right, to the third level. So we know that there are cases that pulse stretching falls short, and we don't have this assumption. So leakage noise is something that we can handle actually quite well. Okay, and what I wanted to show is that actually if we use the same method we have, we get this, that if we do the circuit inverse, there is a term which is first order in the noise, despite doing, and it doesn't matter how many order you do with the circuit inverse, this term keeps popping out. And only if this omega 1 is global depolarizing, then this commutator is 0, and this method works. But in that case, there are simpler things that you can do. There's no need to do these fancy error mitigation methods. Okay, this is just to show how it works, but the noise is more mild. Okay, so this is just two swaps, and you can see, again, this misses the target, and we converge. Probably not perfect because of some residual coherent error.
Is this a simulation or
No, this is experiment. Yeah, it's Jakarta, and you can see here the actual data. Yeah, you can see the actual data, and it's doing it in different times. We got consistently that the mitigation works. Okay. Another thing we can understand is the saturation in performance. Okay, so while we see exponential decay up to a certain stage, at some point this omega 2 kicks in, and we reach a certain saturation. Okay, so this again emerges from the theory, while from this picture it's not clear why there should be a saturation. Okay.
Sorry, Rat?
Yeah.
Does this mean that non-Markovian noise was less than 10 to the minus 5?
Well, this is simulation. This is not an experiment because, okay, I needed to reach such high orders, and with randomized compiling, we don't have that window that we can actually run this experiment. So there was no non-Markovian noise here. So about non-Markovianity, let me comment that it's possible, we haven't done it yet, but to just integrate it with dynamical decoupling. And this method is somewhat complementary because it handles Markovian noise, which has high frequencies, and dynamical decoupling is more suited to low frequencies. So
Dynamical decoupling will remove the zero component noise.
yes, so I'm saying they could coexist this method, and after whatever you get from dynamical decoupling, you remove the non-Markovian contributions, you're left with something, okay, you still have some noise, then you can, as is, implement our method, okay, so they can coexist. Okay, and to get something more and handle a moderate and strong noise, we realized that actually there's no point in using the Taylor expansion. Taylor expansion is approximation that is suitable for a specific point, and here we show the difference between 1 over square root, okay, we use this 1 minus x, it's easier, and the corresponding polynomial, okay, second order. This is what you get using the Taylor expansion or the Richardson. And you can see how it deviates now. If this noise is strong, it doesn't help you that here you're good, if the noise is actually here. So instead, we can choose a specific interval and choose a polynomial that works better in this interval. Okay, maybe it will not be accurate at 0, but overall, it's better. So here's again an experiment with 10 swaps, and this is what we get with the Taylor expansion. And this is what we get with essentially choosing an interval. The way to choose the interval is, it's another measurement, but it's a very lightweight measurement to estimate what is the window. Okay, it's something like 1,000 shots or of that order, because it's not that sensitive to the size of the window. So here's an illustration in simulation. One can understand the differences. So what is plotted here is it's not the noise spectrum, so this is not frequency, it's the noise histogram. So here is strong noise, here is weak noise. So we actually look at the evolution operator, it's simulation. We look at the eigenvalues of this evolution operator, and this is the spectrum of the noise in this simulation. This was 5 qubits, if I remember correctly. So unmitigated, this is the noise we have. Okay? Now, if we run one iteration with Taylor, okay, or the coefficients that also exist in global folding, we get this, which is nice. However, if we do this interval method, which is like the second main ingredient in our method, you see that after one iteration we're here, okay, which is better. Okay, so in summary, if we compare, the closest method, okay, which is also scalable, we use the circuit inverse, the pulse inverse and not the circuit inverse. We understand what is the performance limit. And it was also not clear from this paper whether one should actually run first the inverse and then the circuit or the other way around, okay? So because it was just this counting argument, there's no answer there. And we understand that it has to be this specific choice. If you change it, the method doesn't work at all. It's an issue of time ordering. And also, by doing this interval method, we can handle stronger noise. The last thing I want to say is that we recently realized that we can also handle drift or change in the noise parameters in time, which, as I mentioned, is a big problem for this method. Because it turns out, okay, so how would one naively run this? So let's say we need 50K shots to get proper statistics, the level of accuracy we're interested in. So one way would be to just do the forward evolution, 50K shots, okay? Then do the forward backward. We already have the circuit, so let's run it again, okay? Collect the whole data. And then essentially with the averages, calculate the mitigated value. A different way would be to divide it into sets, let's say of just 1K shots or even less, and calculate K, then another K shots of this, and another K shots of the higher order. And then...
Shots means you actually do the experiment, you get the probabilities from the...
You don't get probabilities, you get 1, 0, 0, 1.
You get shots. You get actual shots that you use to derive probabilities with shot noise.
Yes, yes. So the point is that when doing it like this, of course, this is very noisy, statistically noisy, but the point is that the noise mitigation works here because the noise is stable for this time duration, and it's being cleaned out. And here it's being cleaned out. It's a different noise, but it's again being mitigated. And then one collects all of them together. And just to convince you this is working, this is just a simple simulation.
Blum, you're going to turn into experimentalists. Huh? We call this scatter
by the way, I was one. I was with Moti Seget.
We call this scattershot sampling
okay.
For experimentalists.
I was in my master's until I burned the laser and a few other things.
The IBM devices are implementing the second approach.
Sorry?
The IBM devices that you ran on, they're implementing the shot on the right-hand side. So I think we discussed it once, and this is something we haven't
really, we haven't checked, okay? So, because again, it requires more circuits and we have this limitation, okay? But we expect that it will do some improvement. If there's already shuffling, as you say, it would matter, okay? But that's work to our advantage if it's already implemented, okay? But at least in terms of simulation, we understand that this is the correct thing to do for this method, okay? So if it's already done, fantastic. So here's the actual value. This is like the coefficients of the Liouvilleans, okay? And you see the strong time dependence. This is the ideal value. And if we do it in this naive method of doing everything here, by the way, Hagai, we run it sometimes in different jobs, so sometimes it really is separated. And you see that when we break it to small chunks, there is a certain overhead, of course, but when we, at least in simulation, when we do it, we converge to the correct value. In this case, the noise is such that in second order we converge, but even in first order, it's better. Okay, so to sum up, there's still a lot to explore. This mapping that we did is essentially based on the L2 norm. It's obviously much better than just taking the zero noise assumption, but we're not claiming that this is optimal. It was just the easiest thing to do, and it's analytical, and we have explicit expression for the coefficients. So it's nice to work with, but potentially one can gain another factor of 2 or 3, and every little thing count. We have some thoughts about how to go beyond the second order, but I wish we would be already at this point where this is the bottleneck. Okay, that would be a happy day. And I think there's a lot that can be done with integration with randomized compiling. It can be done more efficiently, and also with dynamical decoupling and so on. And I think for this specific field, it's very important to actually run experiments and not to settle with simulation, because it's a zoo, okay, with real devices. Everything that can happen, happens, okay? And with that, I want to thank you for your attention.